EC 111, Lecture 4 and 5, Set 5, Conditional Operator and Continuous Assignment Statement. Let's take a look into the conditional operator. This is similar to if-else that we've seen earlier, but it could also be used within the continuous assignment within the always block. So the conditional operator that we will be discussing here is actually a ternary operator, which means that it has 3 operands. And it's going to be using these 2 signs, the question mark and the colon. And the syntax is really this. So if the syntax is true, if the clause is true, then we're going to execute the true statement, and if false is going to assign the false expression. How it looks like in real example, for example, we could have assign and output will be equal to P question mark A through B. So what that means is that the output will be A if P is true, and if P is true, then we will have A, and if P is false, we will have B. Here we see an example for this conditional operator. Here, as we've seen earlier, we have the assign. The output is going to be A if this expression here is true, and if this expression is false, we're going to have this B. We could write the truth table for this expression as you see on this slide. And the one thing to remember is that if you AND the bitwise AND, it will return the value don't care, is if one of the operands is a don't care. And the other operand is a 1. Very simply said, a conditional operator is going to be mapped to a mux and a registered output. So if you write this program defining the parameter here, then what happens is that if we are going to assign to the output based on the value of the select, which means that here the select is going to come to a multiplexer, and then the output value will be one of these inputs, D1, D in 1, or D in 2, and then this is going to go to wherever this design is going. In this particular case, we have this assigned to a positive edge of a flip-flop, so this is how the synthesized design will look like after the hardware is generated. However, this is not a general rule of thumb. The conditional operator could also be used with the tri-state buffer because it has the flexibility of assigning a z value in the logic. So in this case, it will translate into a tri-state buffer. Let's see how this would look like. Assume that I have this condition, which upon being satisfied as a true will be either a certain expression or a tri-state buffer. So when we synthesize this, this is going to be translated into a tri-state buffer, which is shown here. So this is another type of selector or conditional operator that is synthesized into hardware. However, if we use the same conditional operator, but we didn't use this for the z value, we used, we use this changing this z value to another value, it will infer a mux. So the tri-state is used for inferring the high impedance value. If you don't have a high impedance value, it will usually translate it into a mux. Even though, not everything is in our hands, some of these construct gives us some capability to manipulate things at a little bit lower level, even though these are mostly behavioral or RTL level constructs. So just reviewing some of our what we've described earlier, the continuous assignment is going to be used for a combinational logic. What it means is that just like any combination where you combinational circuit where you have just wires, you don't have a notion of a register, we have this wire which is connecting the inputs to the output, which means that if the inputs, if any of them changes any time, we're going to reflect that change in the output. There is this difference between how we construct this type of logic with as opposed to constructing the type of logic that is sensitized to flip-flop or which have a notion of time. Only when the clock arrives, we're going to change the output. You could also use this in System Verilog. You can have this assignment delays or you may give it a given strength as we have seen before. But if you don't define delay or a strength, the default value is going to be used. Here's one more information about the left-hand side and right-hand side of the continuous assignment. I'm not going to go through the details in the lecture, but every time you write a program, you kind of need to come back because, if I just define it as a story, it may not make sense. What I just want to emphasize is that there may be a mismatch between the type of, one side of the continuous assignment in terms of the equality and the other. What that means is that, for example, here there is, the most significant bit, which is in this case 5 bit, and this is assigned to a 6-bit wire. But here, because we only have 5 bits, assigned to the 6-bit, then we are going to truncate the higher bit values once we use this type of statements. System Verilog also gives you the capability of defining functions, but because this is inside a continuous assignment, the function is still a combinational logic. So we cannot have a function call where your function is a sequential logic, but you have the capability of calling functions within these modules as well. When talking about continuous assignment, we could have either an explicit continuous assignment, which we define by a sign. We also could just go and declare a implicit net, which can be declared as a continuous assignment. For example, if you have a wire, we know that a wire is a combinational logic, so this is going to be inferred as a continuous combinational logic. And this, when you have this simulated during the simulation, it's just going to be evaluated from the beginning time of the simulation time until the end. Anytime a change occurs, it's going to continuously changing the output. And but the point here, the sticky point here, is that the continuous assignment cannot be used for initial and always procedural blocks where we are talking about sequential logic. However, if you use always which means basically a combinational logic, we could use it. Be very careful because there is this assign statement within the always procedural block is not allowed. So when we have always at A and B here, for example, this is a combinational logic, but we cannot anymore use assign here. It's not allowed. So, but this, if you define the sum as a sum of A and B, this is going to behave like a continuous assignment. Like any circuit can have any type of combinational logic, a continuous assignment can be any number of the combinational logic that are running concurrently. And because there is no notion of time attached to this, this is always going to change as we are changing the inputs. There is no precedence for these procedures. So changing the order is not going to impact how this is synthesized into hardware. For example, if we have a half adder and we are talking about both the sum and the output carry out, doesn't matter if we put the sum first or we put the cout first, it's going to have the same impact as we synthesize it into hardware and get this continuous assignment, which is basically concurrently run. Anytime A and B changes, the cout and sum are going to be changed. So continuous assignment variables that are used within an always add procedural block are going to be generating an error if you use the same variable. So you're going to have an error if the same variable is used for both always and the continuous assign. So here we're talking about, like this example, we generate an error. This assign is using the variable c. C is also used within this always block. This is going to generate an error because it's not going to take the same variable value for continuous and sequential logic. And it also will generate error if the same variable is driven from multiple continuous assignment. This is just like if you connect to the same output wire multiple outputs of a gate. This is going to generate an error if we did it in real life, and because this translates to a piece of logic, this is going to generate error for us in system Verilog as well. More on continuous assignment. If the right-hand side has an array reference with variables, so there are different possibilities for the right-hand side, then we are going to generate a mux, because the mux is going to select between the various possibilities available. However, if this right-hand side is a constant value, like we see here, it's just a specific address, what is going to happen is going to just generate a wire. And we see the difference when we synthesize this into an actual hardware. So we have an array, it's going to select between the array elements, it's going to generate a mux, but if we have like a defined value, it's just going to be a wire, as you can see here. In the appendix, we have listed a number of basic elements and a few more examples. If you're interested to take a look, feel free to take a look. And we will be covering next lecture 6, where we will be discussing more about the Verilog and how it's used for programming real hardware.